cross-modal transformer or cross-modal attention, transformer attention, is that one modality will be the query. That's what I want to encode, language. But I'm going to use, the only thing I can use it for is going to be that other modality. And so I take my language and I'm going to say, hey, in vision, is there anything in vision that can use, could make it so that you can recreate alpha? And that's what it will give me here. With the output of this will be the best I can recreate from just using vision. And the key aspect after that is a residual node, which will say, hey, what is different between this and this? What is different? And whatever is different, add it to me. And that I don't show it here, but that's what is done here, is like it says, whatever is different from like what you like, this is vision, and that's what you could get from it. But now I'm going to say, okay, add it to me. We'll have a residual connection here. And the residual connection is really important because then it will say, hey, from language, what can I add to it? So I didn't put it here, but there will be also a residual connection to allow me. So I will say vision and language, and then what you add to it to the language. So language pre-training, token level and sentence level. And I want, sorry, I just, yeah, I want to language. Yeah, I think I got it correct. Yeah. Okay. Alpha to the beta. Yeah. Okay. Yes. So language. So, but how do you train this? And how do you take and train this in an unsupervised way, hopefully, and then we can look at fine-tuning it eventually. So I do not like it. And so I want to train to be able to generate new embeddings. And so I would like to train it in a supervised way. You probably have the intuition that we will use something similar to the distributional hypothesis. Distributional hypothesis says the meaning of a word can be approximated by the meaning of the other words. So that's probably an intuition. But I want to be able to train my model in such a way to get these embeddings. Or I may also want to train my model in such a way that I get only one embedding for the whole sentence, instead of having to maybe have a, I don't know, an RNN on top of this, or doing a pooling, like a mean pooling on top of that. I'd like to have upfront a language that. And so, and in practice, I will often like pre-train and maybe on a very large corpus of unlabeled data of maybe a word, and then I will fine-tune it to my task. So I will fine-tune it to my task. This could be very simple. I could fine-tune two ways. Usually you fine-tune. So one way is to fine-tune by adding another layer on top, and then whatever you use here, you learn in a general sense, and then you add a few layers. Or maybe what would be even nicer if I could also fine-tune the inside of it, like fine-tune that as well. So that's my goal. And so one very interesting way of training those transformers is called BIRD, bidirectional encoder representation from transformer. And here the idea is there are quite a few advantages of that approach. One is to jointly learn representation for token level and sentence level. So in one model, I'm going to learn how to encode at the sentence level and also encode each individual token. So that's will be something, I mean, maybe yes, sometime I would like to use only one and not the other, and maybe there's a slight waste there. But the nice thing is the same model will give me both. There is also designing this so that the fine-tuning of the will be done with the same model. That's a small thing, but it's an interesting thing. And then one thing that I personally like, they don't people emphasize as much, but this architecture can be extended really easy to get a large corpus, or also get a difference between sentence, because there are tasks where I have a sentence or I have a corpus of sentence, and I just want to get the embedding for each words in the sentence, or I want an embedding for the whole corpus, or like the whole sentence. But there's quite a few cases where I want to compare something together. I want to compare two sentences, like I have a question and an answer, and are they the same? Or two sentences, are they similar? A question and answer, are they related? So this is very interesting to have the same way of learning that will allow me to get also prediction of the joint embedding, one sentence embedding, and if I needed, the same model may be able to do some kind of more relative or differential task. And this is all done in a long-range dependency and bidirectional. So that's the advantage, but that is the advantage of the transformer. So that one is on. So how do we do all of this together? All of this. So what is going to be here? The model. It is a transformer self-attention. But there's a small change. Is now we will add a special character. In fact, two of them. One as the start of the sentence, or like just and then another one as a separators. But that's the only two difference on the input. But how do we train this unsupervised? And so there's quite a lot of extension of how this could be trained. I'm going to share one strategy of how to train this. And the first one is the distributional hypothesis idea. And the distributional hypothesis idea is that if I mask a word, I should still be able to embed it, even if I don't observe it, because I have my context into there to help me. So so in this case, like so what will be the loss in this case if I was to just use this is just how well. So all of these, for this exact sample, the loss will only be defined on these tokens that were masked, and that will be my loss. So the loss here will just be defined on these masked cases, okay? And so how close am I, if this is an embedding, how close that word embedding is to the real ground truth word embedding. That could be one way. Or if it's a one-hot or different version. Now, what the other thing that's interesting is how do you train to get that sentence level embedding? And there are many possible ways, but one way to get an embedding to know if this one is to get we want a loss that will allow you in an unsupervised way get one embedding for the whole sentence. And the one idea that was proposed was is this sentence the next or not, if this sentence the next or not to this sentence. And so this HS will be there and used to like simply detect is it yes or no. And that's one interesting loss. And so the loss in this case is only at this point. Is it the next or not? And you have the ground truth because you have a large corpus with sequence of sentences, and you can simply and the training data, that's the corpus. And then what's really interesting also is that you can start also look at how do you differentiate between different sentences. How does because you have to ask yourself to train this, it has to know that this token is from one sentence and this token is from another sentence. And the normal position embedding will just say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So by default, the position embedding will not, the typical one will not tell you that this is a different sentence than this one. So you can imagine there's a nice simple way, which is just a sentence embedding or segment embedding. So really the input to each of those tokens will be the sentence embedding, which could be just a one hot. Is it the first sentence, 0 or 1? Like, and there's just a linear projection maybe on top of that. That's what will be this. And then the typical position embedding, you could make it sequential, or you could have restarted here. That would be another way. Maybe you could have done it. And then you have the embedding of each word. And that's what you can sum them. That's what they did in the original paper, or you can just concatenate them or do some other way. So this is the way to train the BERT. And then you can use it for different tasks. So you take that has been trained with these two loss functions, and it can be trained in an unsupervised way. And then now you can use it. And now if I ask you a task, and I want a task like sentiment analysis or document classification, how can I fine-tune this? It's simple. You just use this part of the transformer. So you put as input CLS just because that's a token that the transformer knows about, and then you encode your input, and then I am going to ignore all of these and just take this sentence level embedding and just learn, I don't know, softmax or something on top of that. In fact, what you could do is fine-tune only this part, but what they found in practice is that the fine-tuning of this is really, really efficient, very efficient. I mean, give the best performance. And so they will, in fact, only put the softmax here, no linear projection, nothing other than the softmax. And then all the fine-tuning will be here. And what are my weights in this? You have WQ projecting your query, WK projecting your key, and W. So although it looks like a big and complex one, there's only those 3 projection matrices, and the rest, there's a lot of computation, but the number of parameters are not small. I will not have small. It's quite big because you can do it for many different words and all this. But I will tell you why it's big. But if all the sentences you had were always really short, it will be very easy. But the basic transformer requires to know the length, the maximum length of your sentence up front. Now, there's been extension, XLNets and others, to make it almost like a sliding window kind of thing that will allow you to handle that. But the default one will kind of almost have a predefined length of this. And that's a little bit why the big number of parameters. But in general, there's only 3 matrices for each layer that is to train. So that's what you will need to fine tune here. And if we have a label for each token, let's say that we have sentiment for each token, then I can nicely have maybe just a simple projection linear projection here for each of them, just to project my embedding into my whatever label I have here, and then fine tune this as well. And by the way, do you end up having a different weight for CLS? Like W, you remember there's a W for query, W for key, or W for value. Is it different, this W for CLS, than it is for the other words? No, it's not. Okay, so it's not. It's exactly the same W that is used here to embed HS. It's the same W. It's just that the model has learned and it has tweaked the W to respond. So specifically the W query probably is going to be very important in how it embeds the CLS so that it takes it and embed for the HS. So, but it's the same W set of parameters for all of them. And then you ask yourself, another task we could do is how to compare two sentences. Because it was trained in this way unsupervised, it knows what a separator can be used. And so by simply adding that, it should be giving you an embedding. If you didn't have it, that separator, then that embedding would be just a sentence. But with it has the separator, it has learned. So if you wanted to compare two sentences, like natural language inference, that would be an example of that. So I do not like it. It's quite different from I enjoy my time here. And so you can do, and then you can even use the bird, which is really cool, from a question answering. And so question answering, how old is the man? And then you would like to generate, he is 25 years old. That's what you would like to generate. And so, sorry, I should probably have put them here and really have the token start here. Have the token start and have everything shifted. But yeah, so the way to do this will be that you want to input the question and you want to be able to generate an answer. And so how do you do this? You will, in fact, in practice, only one way to do it, let's say question answering, you want to, and this is, sorry, I know, I was correct. I was correct in my slide. I apologize for that. Let me, I was trying to answer a different question. Here, the task, sorry, is not question answering, like writing the question, writing the answer, but the question answering is like, I have a very, very long text. I have very, very long text here. I have extremely long text here. And the idea is that you want to be able to find which part of this text, which part of the text is the answer. And so in this case, then I will use, I can use a nice softmax. What it does, it looks at all the text and say, where is any of them the start? That's comparing the start token with each of them. And you can then see when there is a max value. So is this look like a start? Is this look like a start? Is this looking like a start? So that's my query. Like my query is going to be this in a sense. Look, and then I will use also context. But the H is not just the embedding of the word, but it also contextualized on the questions. So it's context is the embedding of the word contextualized on the question, and that will give me a nice. When you can do the same for the end time, and this is done from fine tuning. Okay, the last part, I have 3 more slides, is how do you do other extension and you will have some of it in your reading. And I invite you to look at follow-up papers that been in that topic. There's a lot of interest there. But the idea of multimodal, how do you do with multiple modality? What if it's not just email, like language, but I also have an image? Like I have maybe, let's say I have unsupervised data, which is not really unsupervised, but it's paired data. I have this paired data between captions and images, and I would like to learn a nice embedding. The simple way is to just concatenate everything and make it as a self-attention. That will be one way, like a self-attention. But how do you train it? Then you can do the same idea as distributional hypothesis, and you mask certain word, and in that case, that gives you the loss. Or you can also mask or zero out part of the image and also try to see how well you can either regenerate or extrapolate it. So can you, from this part, be able to regenerate this part, for example? A lot of it will be done at the object level, so they will not take the whole image and just randomly slice it, but instead they may just do it at the word level. Another way that builds a little bit from that intuition I talk about, I think in Fusion, I believe I talk about it, is that sometimes you have one modality that is stronger than the others. So language may be stronger or more relevant, not stronger, but more relevant to the task. And so in that case, you could embed your word in such a way that the word is the most important, but you're kind of contextualizing acoustic and visual. And then after that, do the multimodal self-attention like a bird. But as a pre-step, it just does so it's one other way to do the embedding as well. So I'll let you read other ideas on these multimodal transformers. I think one of them is for dialogue that we suggested, and I think was visual BERT, and some of them are also optional. So thank you very much for your attention.